last time, we need to solve our computing problem number 9, greatest common divisor. And we recall the middle school procedure using the prime factorization. Yeah. Although it is, from the procedure point of view, it is simple, but it relies on prime factorization. And later, I explain this prime factorization could be very slow when you need to factorize a large integer. So how large? I use this 1,000 digit example, this large, then it could be as slow as a few months, that slow. Yeah. All right, so that's what we were last time. Yeah. Later, if I have time, I may talk about, this prime factorization, because this slow, here, let me write, prime factorization, very slow. The slow prime factorization, this fact could be useful, in encryption application. Yeah, so that's very interesting. Yeah, later when I have time, I may talk about, this story. Yeah. All right, so let's continue to the next slide. So this time, we need to solve it in a more efficient way without using the prime factorization. Yeah. So that's the goal. Yeah. Right. But how to do it? How to make it faster? How to get around the prime factorization? Yeah. The idea is simple. Yeah. Idea, although here I put a goal here, but the idea is also like this: reduce the problem size. So we have seen different ways to reduce problem size. Here, another way. If you look at the title of this part B, we call it variable size reduction. Variable size reduction. Yeah, so that's what we are going to have. Yeah. To do that, yeah, so you ask the question, how to reduce the problem size? Yeah, that's the critical part. Yeah. To do that, we need to use a mathematical tool. Okay, some special mathematical tool to help us. Yeah, so you may feel, we may need some fancy math tool, but actually that tool is very simple. So what's that? Division algorithm. Division algorithm. How to do integer division? You know how to do, right? Yeah. Everyone knows how to do integer division. And we use that integer division here. And we give it a fancy name called the division algorithm. The integer division is so simple, but people still give it some formal name, division algorithm. Yeah. This name appears in number theory. Number theory. Okay. Yeah. So here we use the number theory version division algorithm. What's that? Given positive integers a and b, b is not equal to 0 because we want to use b as the divisor. The divisor cannot be 0. Yeah. So we can make this assumption, b not equal to 0. Yeah. Then the conclusion part. There exists unique integers q and r. Q for quotient, r for remainder. So quotient and the remainder part. Yeah. With the remainder must be in this range, greater or equal to 0, less than b, strictly less than b, such that a equals b times q plus r. This is the so-called division algorithm. Yeah. So here you can see we just formulate the usual integer division in this way. Nothing fancy here, right? So plain, so simple, but so useful. In number theory, this division algorithm is extremely useful. Okay, yeah. Many advanced theorems are developed by this division algorithm. Okay, yeah. Here, to find the greatest common divisor, we need to use this tool. Yeah. How to do it? Yeah, let's do it. Let's connect A, we replace A by M. We replace B by N. We do integer division. Okay, yeah. All right, so then, yeah, but here we make some small assumption, M greater or equal to N greater than 0. Yeah. If not, we switch, yeah, because you may ask, how about when we are given arbitrary two integers, how about N greater than N, right? We just swap. If that happens, we swap N and M. Then our first integer will be greater than the greater or equal to the second integer. So we will have this assumption. Yeah. All right. Yeah, the reason we want the first integer greater than second one, because for problem size reduction. For the reason is for the problem size reduction. Yeah. Yeah. So what is the problem size here? Now, you may ask that. So what is the problem size for this question? Yeah. In this question, the problem size is the maximum of M and N. So when we do problem size reduction, we want to reduce the maximum of these two numbers. Yeah. All right. Yeah. All right. So here, to do the problem size reduction, so let's start with this version after we apply the division algorithm. Okay. Yeah. All right. So the next step, in order to see how do we reduce the problem size, we need to do transformation on this formula. Okay, yeah. To do transformation, yeah, we start with the GCD of M comma N. That's our goal. we need to calculate this function. Yeah. So when we start, we replace m by this new expression, nq plus r. Yeah, so we get this expression. The question, we want to simplify it. Simplify it. Yeah. Mainly here we see there is a term that is a multiple of n times q. It is a multiple of n. Can we do some simplification regarding this multiple of n? Yeah, we can see it. Let's look at this fraction. Left-hand side m over n. Yeah. The reason we consider fraction, you may ask why we consider fraction here, because we want to do cancellation, right? Yeah. So we want to do simplification. Let's say we want to do simplification. Yeah, not necessary cancellation. Yeah. Simplification. When we do simplification, because m equals to that nq plus r, so the nq multiple over m, we get the quotient n out. Then remainder r over n, that's the fractional part. Q, the integer part. R over n, the fractional part. Yeah. So after this transformation, yeah, this is our transformation, or part of it. Yeah. After that, you can see the integer part would not do anything regarding the fractional simplification. Yeah. Think about it this way. When we do cancellation, this integer part does not have any impact on the cancellation, right? Yeah, that's the integer part. Nothing to do. There is no impact on the denominator, right? Integer does not put any impact on the denominator, right? Yeah. Yeah. From that point of view, so you can see the GCD of m comma n, the same as the GCD of r and m. So that's this one. Yeah. The Q part, new contribution to the GCD. The Q part, the m multiple part has no contribution to the GCD. Yeah. Because the GCD is the greatest common divisor, right? Greatest common divisor, when we do cancellation, we cancel greatest common divisor, right? M over n, if you want to make this fraction as simple as possible, you cancel out the greatest common divisor, right? Yeah. But that Q quotient part, it's an integer. It's integer. The integer part has nothing to do with the divisor cancellation. Think about that, divisor cancellation, okay? So nothing to do with the divisor, so we can remove it. Yeah. So this version, that's the after the removal, integer part removal. So we get a GCD of m, and this time size reduced. The size is reduced. Okay, yeah. The size, this time, size is n. Yeah. Before reduction, the size is m. After reduction, the size is n. And we assume m greater or equal to n. Okay, yeah. So it is reduced, although there is a m equal to n case, but that won't happen frequently. Most of the time, n greater or equal to n. Yeah. All right. So this is the key property. Develop a key property. What is the key property? This is the key property. The problem size reduction formula. This is the key property. Okay, yeah. Now we apply this key property, we can solve this GCD problem. Yeah. Okay, yeah. So we, yeah. And we can keep doing, yeah. This is only one-time reduction. Can we do second time reduction, third time reduction, and so on, until we cannot do it anymore. Yeah. If we can do, we keep doing it until we cannot do it anymore. Okay, yeah. So the algorithm that way, that method is called Euclid's algorithm. Yeah. Euclid, about 2,000 years ago, 2,000 years ago, Euclid wrote a, famous book volumes, yeah, several volumes. So it's just called books, okay? As I remember, yeah. And inside it covers, all the basic math theory, geometry, number theory. Yeah. And this Euclid's algorithm was one of the main results in that book's volume. Yeah. Yeah. All right. So that's just like the rule is as simple as this one. When you calculate the GCD, if y equal to 0, because we do not allow x, y both 0. Remember? Yeah. Remember the condition. Yeah. We do not allow x and y both 0. Yeah. Later I will explain that. Yeah. So here y could be 0. If y is 0, then the answer is x. Okay. Yeah. Yeah. Because we assume x not equal to 0 by the initial assumption. Yeah. If otherwise, yeah, if x mod y, this is modular operator, okay, percent. If x mod y equals 0, that means x is a multiple of y. Okay, x a multiple of y. Then the answer is y. So that's two base cases. Otherwise, problem size reduction. Okay, we put the y as the first variable in GCD. The second variable we use x mod y. The size is reduced in that way. Okay, yeah, and we keep doing this until we get to the base cases. Yeah. Because finally, we need to get to one of the two base cases. So we stop. Okay, we stop. All right, yeah. That's the famous Euclid's algorithm. Famous. Yeah. Very important in number theory. Yeah. This algorithm is important, fundamental in number theory. Okay, yeah. All right. For us, we use this algorithm. We can calculate GCD without using prime factorization. The great thing of this one, without using the prime factorization. That's the best thing we have from this algorithm. Okay, yeah. Then its direct consequence, it will be much faster. It avoids prime factorization. Yeah, think about, even we have 1,000-digit, 2,000-digit integers. Yeah. So imagine 2,000 digit integers. Yeah, we want to calculate GCD of these two numbers. Because by applying Euclid's algorithm, we do not need to do prime factorization. And basically, we just do integer division, modular operation, integer division. That's much faster than prime factorization. Okay? Yeah. So although you need to do many, many times, you know, the size could be reduced quickly. Okay? Quickly. Yeah. Yeah. And you can get your answer very fast. Yeah. It's very interesting. I make a programming project on this one. Yeah, but I may like to make it as an optional. So if it's possible, I make it optional. Yeah, because our formal project, I have another topic for the formal project, you know, the Fibonacci numbers. Yeah. Next, I will go to the Fibonacci numbers. Yeah. Yeah. And this one, it's an interesting problem. Yeah. Not too hard. The thing is, if you need to implement Euclid's algorithm, that's easy. But at the same time, you need to compare it with the prime factorization method. Yeah, you need to do comparison. Yeah. So the prime factorization, yeah. Actually, I have one example, prime factorization. I used it last semester. Okay. So I can give you that example last semester. Yeah. Last semester, when I remember when I tested do prime factorization on 16-digit number, 16-digit integer, no, it's not very slow. No, 16-digit, still a few seconds. But larger than that, you know, 20-digit, only 20-digit prime factorization, extremely slow, you know, running forever, never stops. Only 20-digit, not 1,000-digit. Think about the huge difference. Not 1,000-digit, only 20 digits. Yeah, it never stops. Okay. Yeah. I do not have the patience. You know, I have to kill the program. Okay. Yeah. All right. Yeah. So if you are interested, later I can post my program so you can do experiments by yourselves. All right. Yeah. Yeah. So the recursion, yeah. So right, size reduced. Yeah, we know that. Okay. All right. Yeah. Next topic. Yeah. Remember, I have one problem left. B.3, general solution of the binary bits problem. Okay. Yeah. And in this one, actually, we need to do a lot of math. Yeah. Let me see. Yeah. Remember that count binary digit, that problem. we did a special case where n is power of 2. Yeah. So what we did, n power, yeah, let me put here, n power of 2. Okay, we did that part. Yeah. Now we need to consider the general case. Yeah. Yeah, but here you can see I need to do a lot of math. Yeah. The strategy, guess, and verify approach. Actually, we need to apply mathematical induction here. To verify, we apply mathematical induction here. So that's what you learn in discrete math. Discrete math, mathematical induction, very powerful tool. Yeah. All right. Yeah. But I may like to delay a little bit. Yeah, because this mathematical induction later when I work on Fibonacci numbers, I will apply mathematical induction another time. Yeah. So this one, yeah, to show, because this is our guess, we need to verify this guess is correct. How to verify mathematical induction? Okay, yeah. Yeah, but today, today I may like to skip this part. Yeah. All right, yeah. So that's the, detailed work. Yeah. I may like to skip this part. Okay. Yeah, so that's the details here. Okay, yeah. Later, let me see. If I feel necessary, I may go through this part again. Yeah. Otherwise, if we do not have enough time, we just skip this part. Yeah. Yeah, because today I like to start next topic. Next topic in module. Yeah, let me see. Module 4, right? Yeah. Let me check my PowerPoint slide. Yeah. Oh, this is part B. Not module 4, still module 3, but for the part D of module 3, Fibonacci numbers. Yeah. We still, our second big topic in this module, Fibonacci numbers. So let's start with that. All right. Okay, yeah. D.1, introduction to Fibonacci numbers. Yeah. So it's a very famous problem. Yeah. And there are many ways to calculate Fibonacci numbers. Yeah. Our problem 10, calculate Fibonacci numbers. First definition. Yeah. Many of you may already know it. Yeah. Here, I just recall, given recursion formula. The recursion formula is very simple. The base case is two base cases, F0 equals 0, F1 equals 1. The recursion formula Fn equals Fn minus 1 plus Fn minus 2. That simple recursion formula. But the numbers generated, we call Fibonacci numbers. They have so many interesting properties. Yeah. And I remember there is some book, the whole book talking about all the advanced properties of Fibonacci numbers. Some properties very complicated, very hard to prove. Yeah. All right. Here, our problem, we need to find Fibonacci numbers F sub n efficiently. There are many ways we can find Fibonacci numbers. And we want to find some fast way for the Fibonacci numbers, given n. Given that capital N problem size, we need to find f sub n. Yeah. All right. Here I list first a few Fibonacci numbers. Yeah. So you can see, yeah, it is not easy to find some simple rules. Yeah. The pattern, yeah. Can you see any pattern? Yeah. It's hard to see any obvious pattern here. Yeah. All right. Yeah, the reference in our textbook, section 2.5, page 80. Our plan, yeah. Yeah. Because we need to learn some interesting properties. Yeah. So we make our plan. Yeah. The first time we solve it algorithmically. Yeah. So we use computer algorithms to solve this problem the first time. Yeah, but the second time, yeah. So that's the, write a computer program to implement some algorithm. Yeah, that's first way. Second way is solve it mathematically. Yeah. Because if we can find a math formula, then using the math formula usually much faster than without formula. We have to implement it using some computer algorithm that most of the time algorithmic way won't be as fast as the formula way. Yeah. So for that reason, if it's possible, we try to find a formula for it. Yeah. For this example, yeah, we can find. Although we need to do a lot of work, but we can find that formula. Derive a math formula. Yeah. All right. There is a simple implementation. Recursive function. We create a recursive function, integer Fibo, and that's the problem size, and two base cases, these two base cases. Then after that, just recursion. So you can see this implementation is so simple. Yeah. But the problem, although it is simple, how fast it is. We need to consider the efficiency of this algorithm. Yeah. This recursive algorithm. Yeah. It solves the problem correctly. Yeah. So the answer generated by this function is correct. Okay, yeah. But the question, is it a good implementation? Yeah, we need to think about it. We need to do some analysis or do some experiments. Sometimes we need to do experiments. Is it good? Yeah. Yeah, the answer, it's a horrible implementation because extremely slow. Yeah, why I use this, strong word, horrible, extremely slow. Yeah, because its growth function, I mean the growth function of the algorithm, its growth function is an exponential function. Okay, exponential function, something like a to the nth, a greater than 1, like that. That's what I mean horrible, extremely slow. Okay, yeah, yeah, we will see that. So why it is, its growth function is an exponential function. Yeah, we will see that later. Yeah, all right. But we want to understand why it is so slow, right? Yeah. So here in this slide, I want to explain why our first implementation is so slow. Yeah. Let me draw a recursion tree. Yeah. To show you the reason. Yeah. I just calculate Fibonacci of 6. That's a small number. Fibonacci number for n equals 6. Yeah. For this small number, if we use that recursive function, look at what is the recursion tree we need to draw. Yeah. Let's do one by one. In order to find Fibonacci of 6, we need to find Fibonacci of 5 and a Fibonacci of 4 first. All right. Then, in order to find Fibonacci of 5, we need to find the values for Fibonacci of 4 and Fibonacci of 3. Yeah. This side, Fibonacci of 3, Fibonacci of 2. All right. So then, keep doing. We need to get all the values when we reach the bottom. The bottom means we need to use the value of Fibonacci of 1, Fibonacci of 0. They are the base cases. Okay. After we apply the base cases, we can get values of all those Fibonacci numbers. Yeah. And then we can backtrack to get to the root of this recursion tree, and we find the value of Fibonacci of 6. We use this tree to interpret, to explain the details of that recursion implementation. Okay, can you see any obvious property from this tree, recursion tree? What's wrong here in this recursion tree? Can you see something not quite right in this tree? Yeah. All right. Yeah. Yeah. Let me show you. Yeah. Observation. Look at Fibonacci of 2. How many times do we need to calculate Fibonacci of 2? You can see 5 times, right? In order to calculate Fibonacci of 6, based on the recursion, we need to calculate Fibonacci of 2. This same number we need to calculate 5 times. Okay, yeah. 5 times. Is it necessary? The same number, why you calculate 5 times? We only need 1 time, right? We only need to calculate 1 time, not 5 times. Okay, but we did 4 redundant times calculation. After the first one, the remaining 4 times calculation all redundant. We should not do the redundant calculation. Yeah. Then you can imagine when the Fibonacci number is big, yeah, not too big. Here I just consider Fibonacci of 100. Can you imagine how big is the tree? Yeah. If the root is Fibonacci of 100, the recursion tree is very big. Yeah. Nobody can draw this full tree, right? Yeah. And if you imagine how many times do you need to calculate some smaller Fibonacci numbers in this recursion tree, large number, right? That's the reason this implementation is extremely slow. All right. And if you do experiment, extremely slow. Okay, yeah. So that I make it our second programming project. Let you feel about it. Let you feel, how slow it is using this direct recursion way. Yeah. And actually, you cannot do fiber of 100. Okay, if you do fiber of 100 using the long integer type, long integer type, you get overflow. Okay. Even the long integer is not big enough to represent fiber of 100. Think about that, how large it is. Okay, yeah. All right. So you will see it in our second project. Okay, yeah. All right. The problem, too much redundant calculation. That's the reason it is bad. How to improve it? Yeah. If you know the reason, then the idea to improve it, remove the redundant calculation. Just remove the redundant calculation. All right, yeah. How to remove? Yeah, that's next question. First, we know we need to do redundancy removal to improve the efficiency of this algorithm. Yeah. The next question, how to remove, how to avoid redundant calculation. Yeah. How to improve method one, yeah. Iterative algorithm. Yeah. We do not use recursion, yeah, because that recursive algorithm gives us the huge redundancy. Yeah. If we do not use the recursion, then we can avoid it. Yeah. And here we can use this iterative method. F of 0, so we create an F array. F of 0 equals 0, F of 1 equals 1, then we calculate the array elements. Okay, one by one. Yeah. From 2 through n, but every time we just do one addition. We just do one addition. We know using computer, addition is very fast, right? Addition is extremely fast. And this method, no redundancy. You can see each F number we only calculate once, no redundancy. No redundancy, right? Yeah, that's good. The result, very fast. How fast? How fast? I can give you an idea if I use the asymptotic notation. Now, we use asymptotic notation. Big theta of n. Yeah. Big theta of n. Yeah. How fast it is? C multiple times n. C some constant times n. Okay, yeah. C times n. Comparing the previous recursive implementation, exponential function with a greater than 1. How big is the difference? Okay, yeah. So this is our first way to avoid redundancy. Okay, all right. Second method, this one, we keep that recursive algorithm. Yeah. But we do some modification. If we can avoid redundant computation, we can still keep that recursive algorithm. Yeah. So you may wonder why we still keep recursive algorithm. So we know recursion idea is very powerful. Sometimes we need the power of recursion, right? Yeah. So last time I showed you the Tower of Hanoi problem. We need the power of the recursion. So we don't want to throw away the power of recursion. Okay. Yeah. So for that reason, we just do some simple modification to avoid redundant computation. Yeah. Here, let me show you how to avoid it. Yeah. The modification is very simple. Yeah. All right. Use an array to store calculated values. Our goal, our principle, we only want to calculate each Fibonacci number once. So that is our principle. Okay, yeah. So how to avoid more than once calculation? Yeah, so the method is this one. Use an array to store calculated values. The next time when you need to calculate that value again, because you already have it stored in your array, why you need to calculate another time? Yeah. That's the idea, simple idea to avoid redundant calculation. Yeah. Make sure that no value is calculated more than once. Yeah. You only need to check your array if you have already stored that value or not. If that value is not stored in the array, then you need to calculate it. That's the first time you calculate it. But if you find there is a non-zero value already there, that means you have the value already. So you just retrieve the value from the array. Do not do recalculation. So that's the basic idea of this second method. Yeah. The second method has a fancy name called dynamic programming technique. It's the topic in our chapter 8. Yeah. For this class, I do not have time to talk about dynamic programming, but here using the Fibonacci number, I give you a short introduction to the dynamic programming idea. Yeah. All right. The essence of this method, yeah. No repeated calculation with this method, store calculated values. Yeah. That's the essence of the dynamic programming. Okay, yeah, all right. Yeah, here, let me implement method 2. Yeah, implement that idea. Yeah, because you may ask me how to store calculated values. Yeah, here, I show you. Yeah. Yeah. And this method is also called a dictionary method. Yeah. Why we call it dictionary method? Because we use the array we use an array as a dictionary. Why dictionary? Because we need to look up for some number, calculated number, lookup. Okay. lookup here, lookup for what? For that Fibonacci number, for a Fibo number, right? Yeah. After we find one Fibonacci number, we store it in a dictionary. We call it dictionary because later we need to look up for one particular Fibonacci number in it. Yeah, so that's the reason dictionary method. Yeah. All right, so the property, yeah. Recursive algorithm without redundant computation. So the dynamic programming, when we use the dynamic programming technique, we use the recursive algorithm, but we find that we use the dictionary method, we can avoid redundant computation. Yeah. Use an array to store calculated value. So that's the dictionary that we're talking about. Yeah. Make sure that no value is calculated more than once, because we need to check if a requested value is already calculated in our dictionary. Yeah. So that's the basic idea. Yeah. Now our implementation is like this. Yeah. We create an array called a known F array. Known. The values are known. Yeah. After you store Fibonacci numbers in this array, they are known. Since they are known, we should not calculate them second time. Yeah, that's the meaning. Okay, all right. Then checking step. How do you check if a Fibonacci number is known or not? You check the condition. No known f of I is greater than 0. Yeah, because when you do initialization, you initialize all the values in this array 0. Yeah. But after you assign it a positive Fibonacci number integer, yeah, this is assignment. Assign S you calculated, because S you get from here. S you can assign to the known value, but you only need to assign it once. The next time, after you assign one Fibonacci number to one position in this value, it becomes positive, right? So the next time, you can return that value directly. You do not need to recalculate it. Yeah. So this way, this condition check, you guarantee each value, Fibonacci value, is only calculated once. Yeah. So that's the first line, has that property. Okay. After that, two base cases, then still we keep the original recursion. Original recursion we only use when that value is unknown. The Fibonacci number for that size n is unknown. Then we call the recursion. Yeah. But when we call the recursion, this recursive function may need to use the dictionary to return the known values. Yeah. That's the way we avoid redundant calculation. Because these two numbers, very likely these two numbers both come from the dictionary. Okay? Not from repeated calculation, from the dictionary directly. Yeah. So that's the reason we can save time. Okay? Yeah. So if you implement this algorithm, the efficiency still big theta of n. Okay? You can see very good. Yeah. Although a little slower than method one. Yeah, method one iterative should be a little faster than this one. Yeah, because this one you use the recursion, right? Recursion way, usually we need to use more resource. The stack could be deep, right? Yeah, so we use more resource than our method number one. So method number one should be a little faster than method number two. Yeah. Yeah. But we still, because method number two, we keep the power of recursion. For this problem, because it's simple, so we may not need the power of recursion, but for the general real world problems, we cannot avoid recursion. Yeah. Because the power is much bigger than the extra resource it is used. Yeah. All right. Yeah. So we finished the discussion of the and the dynamic introduction, the first introduction of Fibonacci numbers, and then also introduction to dynamic programming, the basic idea. All right. Next, we need to calculate the Fibonacci numbers, or we need to, find the formulas. Find the formula for Fibonacci numbers. Yeah. And here we need to start with golden ratio concept, because in the formula, we need to use the golden ratio in that formula. So you can see, some very special thing. Yeah, the golden ratio. Yeah. Most of you heard of that golden ratio. Yeah. So let's look at that. Here, so the golden ratio. So you can see. Yeah. So not golden ratio. Here, the Fibonacci number. Look at this. 1, 1, 2, 3, 5, 8. Are they Fibonacci numbers? Yeah. They are first few Fibonacci numbers. Yeah. We just skip 0. Yeah. We do not include the 0. Yeah. So when you draw squares, yeah. 1 corresponds to f of 1. The second one corresponds to f of 2. F of 2 also equals to 1. Yeah. So you put a square with side 1 back to back with alignment. Yeah. Then the next Fibonacci number 2, you can see you can align well with the first 2 squares. And after that, square with side next to Fibonacci number, that's 3, you can align well with the previous few squares with sides as Fibonacci numbers. You keep doing like that, so you can get a rectangle. Yeah, you can get a nice rectangle. The interesting property from this rectangle, if you draw a quarter arc, yeah, so an arc, 90-degree quarter arc, yeah, quarter circle, yeah, it's a quarter of the circle, okay? Whole circle, you just take 1/4, that arc, yeah. For each square, you draw that arc, so you connect them, so you can get a nice spiral curve, yeah, nice curve, and you can find that kind of curve in the Mona Lisa painting, yeah, in this way, okay? Yeah, so some pretty interesting property, yeah. And that one also related to the golden ratio number here, okay? All right, yeah. So here, yeah, I still have a few minutes. Let me derive this golden ratio first. Now, so how to define a golden ratio? Now, we use line segment. Now, when we start, we use two line segments, one longer, one shorter. The longer one is A, shorter one is B. Yeah. Then we put it together to form A plus B line segment. Yeah. Then we require this condition, the ratio condition. A over B equals A plus B over A. Yeah. So that's the, ratio. Yeah. So why people assume this is assumption? Why people make this assumption? Yeah. Yeah. Because those people, they feel this is some natural way to connect these line segments. Some beautiful way. So ancient people, they feel this is a beautiful way to connect these line segments. Okay, yeah. Then we try to find the ratio A over B. What's the ratio A over B? Yeah. So after we simplify this A plus B over A, we get expression 1 plus B over A. B over A. Okay, yeah. So our goal, we want to find this ratio, A over B ratio. Okay, yeah. How to do it? We make this ratio or this fraction a variable X. Then we find this X. Yeah. Because here, A over B, we need to deal with two variables, A variable and a B variable. Yeah. But we only have one equation for two variables. Then it's not easy to find a solution. Yeah. So we want to convert it to a one variable equation. Yeah. We just make this ratio as one variable X. After that variable substitution, we can simplify our ratio equality in this way. Yeah. Because here we observe B over A equals 1 over X, the reciprocal of X. So we can get an equation X equals 1 plus 1 over X. This equation only has one variable. And we feel we can solve it easily. Yep. One variable, one equation, should not be too hard to find a solution. Okay? Yeah, we can simplify this equation so we get a quadratic equation, x squared equals x plus 1. Yeah. All right. So next, let's try to find a solution. We solve a quadratic equation. There is a formula, right? Quadratic formula. Yeah. For the general case, we have a quadratic formula ax squared plus bx plus c, but to make sure it is a quadratic equation, we assume a not equal to 0. Otherwise, it's a linear equation. Yeah. And the formula for the solution, two possible solutions. Yeah. Negative b plus or minus square root of b squared minus 4ac. So that's the numerator, and the denominator 2a. Yeah. Here in this question, our a is 1, b is -1, c is -1. So we can plug in these three coefficients into the quadratic formula. So we get two possible numbers, 1 plus or minus √5, then the whole thing over 2. Now, but remember, what is our x? When we assume x, that's the ratio a over b. And a and a B, they're the lengths of some line segments. Yeah. A and a B must be positive. A over B also positive. That means we only need positive solution for this equation. So we drop 1 minus root 5, because 1 minus root 5, it's negative. So we drop the second possible solution. So we keep the first one, x equals 1 plus root 5 whole thing over 2. Yeah, so we find that solution. Yeah, but this number, approximately 1.618, yeah, and the people call it golden ratio, and they use the Greek alphabet phi to represent this golden ratio as a notation. Yeah, we know pi, right? Yeah, the meaning of pi, but here golden ratio, another Greek letter phi for it. Yeah. Okay. Yeah. All right. So yeah. So this with the golden ratio notation, then the Fibonacci number can be represented using some magic formula. So why magic? Yeah. Yeah, because it's quite unusual. We know Fibonacci number is an integer, yeah, but the formula representation, you have root 5, you have phi is a number like that, but you put them together, you will get an integer. Yeah. And it connects to the golden ratio number. So you can see, quite special. Yeah. Yeah. All right. So here the formula, the question, how to show it? We want to show it is correct, right? How to show it? Okay. Yeah. Yeah. Mathematical induction. Yeah. We will do that next time. Yeah. Next time. So mathematical induction, I may just do once. Yeah. So that count binary digits, that one, yeah, I have a chance to save some time. Yeah. So if I skip that part, yeah, I just do mathematical induction for this Fibonacci formula.